So here is an alternative definition of Bayesian games that is essentially identical mathematically, but presented differently. It's based on types, or more fully epistemic types. And the type of the agent is supposed to capture everything that's private information to the agent. So if you look at the first definition of Bayesian games that we saw, having to do with uncertainty about types and the common prior, then the type of the agent was her private signal, that is the information set in which the chosen game lies, as well as everything that emanates from it, namely her beliefs about what the possible information of the other agents are, and information of the other agents about herself, and so forth. So all of that is folded into the notion of a type. So that's mathematically very convenient, packing all this information into a type. Formally speaking, then, the Bayesian game is defined as follows. It's defined as this tuple that is as follows. We have a set of agents. We have the actions available to the agent. So now we don't have sets of games. We have very directly the actions available to the agent. And now we have the type, this abstract mathematical object that captures the private information of the agents. So we have a type for each agent. And we have a common prior. As in the first definition of games, we have a common prior, but now it's not over games, it's over types. So each agent has a type, and that prior is common. The type is chosen according to a probability distribution that's commonly known by all the agents. And each agent knows their own type. Therefore, they also have a posterior about the type of the other agents, and beliefs about what the other agents might believe about their own type, and so on and so forth. This is the type of the agent, and we have the utility function now depend not only on the actions taken by the agents, but of their type. That's the formal definition. Again, it's mathematically, in some sense, very simple, but the intuition is complicated because the notion of a type packs into it a lot of things. So let's see it in action. Consider this game that we saw when we discussed the first definition of Bayesian games. Again, we had 4 possible games being played, chosen at random by nature according to this prior, and we had the private signals, the information sets that the agents found themselves in. Here is the type perspective on this. So what are the actions available to agents? Very simply, the row agent has the up or down actions, and the column agents have the left or right actions. The payoff, however, will depend on their type. So let's look, for example, what happens here. So what is the payoff when the row agent plays up and the column player plays left? Well, that depends. If the type of the agents is this one, well, what is the type? The type corresponds now to this information that they have. And the type of the second player is this. Well, what's the payoff then? Well, the payoff corresponds now to this cell right there, is what happens when they play up and left. And so you get 2 and 0 when the types are as they are. Let's take some other random example here. Let's clear the slide. Let's take some other example here, clearing the slide. And let us look, for example, at down and left. when the types are these? Well, what is the types? So the type is this one right here. So this is the information available to the first agent. The second agent has this information available to her, which means that this right here is the game being played. And what is DL? DL means that we're playing down and left, so it would be this one. And therefore the payoffs will be correspondingly 0 and 0. So you can look at other examples and figure out what the type-based formulation means by just taking some random row here and figuring out why the row is the way it is. The last thing to say here before we move on to analysis is that in this particular example, by fixing the type, you ended up with a very specific game. And this is a complicated topic where, in fact, if you wanted to map it to uncertainty over games, you may not have a unique game, and you need to look at the set of games and the expectation there. But I'm just flagging this as a topic. What we discuss will give you a good handle on the two formulations of Bayesian games: the explicit listing of games and a common prior over them, and a partition structure for the agents, or the type-based formulation.
Hi folks, this is Matt, and we're going to talk a little bit now about Bayesian equilibrium and an equilibrium concept, a solution concept for Bayesian games. And the idea of this, it's also sometimes referred to as Bayesian-Nash equilibria. The concept goes back to John Harsanyi in the late 1960s, 1967 and 1968, where he developed this concept. And the idea is that each player now, when we're talking about a Bayesian game, players have these types which determine their payoffs and relate to the uncertainty and can actually tell them something about what they expect other individuals' types to be. And an equilibrium now is going to be a plan of action for each player as a function of their types. So it's going to say, okay, if I observe a certain type, what am I going to do in the game? And it should be maximizing their expected utility. So it's going to be a best reply. And what are they expecting over? Well, now instead of just in the Nash equilibrium, you fix the strategy of the other player and then you just maximize your payoff. Here we're expecting over the actions of other players. So here we've got a situation where we have to be figuring out based on what we expect their types to be and possibly how they might be mixing, how are they playing based on those types, what does that lead to the expected action distribution you're going to face. And in terms of the types, the other player's types can actually also enter into your payoff function. So your utility can depend on information that other people hold. So it might be that somebody else knows about, say, the value of a stock, and I'm trying to invest based on what information I have, and I realize that other people are going to have other information, and that information could affect the value to me as well of a particular asset, for instance. Okay, so given a Bayesian game, we've got our set of players, actions, the type space, probability distribution over the type space, and utility functions. And for the definitions we're going to provide here, we're going to take these to be finite sets of players, finite sets of actions, finite sets of types, and finite sets of strategies. Okay, and when you start going to infinite sets and continua, you have to be a little more careful about some of the details of defining these things, and in particular, measurability kinds of considerations of and integration of things. So we're going to stick with a finite set where the basic principles and ideas will be fairly easy to understand, and extensions to these are fairly straightforward, although there's some technical details you have to worry about. Okay, pure strategy. What's a strategy for a given player? A player's strategy now is a mapping. So S sub I, which says as a function of your type, what's the action you're going to take. That would be a pure strategy in the sense that you're just picking an action for each type. A mixed strategy is then the obvious extension here, where instead of picking a pure action, you're picking a probability distribution over actions as a function of your type. And one thing that's going to be useful then is that if we have a particular type, we can then talk about what the distribution over actions is. So under a mixed strategy S sub I that person I plays, what's the probability that action AI is going to be chosen by them if they happen to be of type theta I? So we use that notation in some of the calculations. Okay, now when we start talking about Bayesian equilibrium, now we have to talk about what a person's expected utility is when they're making their choices, and there'll be different timing that we can think of. So one is ex ante. I have to form a plan for how I'm going to behave, but I actually don't know anything about anyone's type, including my own. So we might think of this as, for instance, a company forming a long-term plan for how it might, say, bid in a series of auctions that are coming up, but it hasn't actually gone out and collected information yet, and it hasn't actually seen the values of other players and so forth. So it hasn't done any of the calculations, but it's trying to form a strategy of how it's going to behave. Second possibility, interim stage. So a person knows something about his or her own type, but not the types of other agents yet, or the other players. So this is a setting where you have seen some parts. I've done my homework. I know what I've seen, and I have to form a strategy to bid in an auction, but I don't know what the other players have seen. And that information could be valuable not only in determining what their action is, but also in determining whether or not I want to go ahead and follow a certain behavior or not, based on what my payoffs might be, contingent on what information they might have. And the third one is ex post. So everybody knows everything about everybody's types. Now, ex post is the relatively least interesting in the basic sense of the kinds of calculations we're going to be doing, because in that situation, if the peoples are making their choices ex post, then the game is going to boil down to just the complete information games we had before. Now, if people have to make their choices ex ante and they still want them to work ex post, then that's a different story that we'll talk about a little later. Okay, interim expected utility. So let's talk about the expected utility that a player has if they're at the interim stage. Well, we can say, what does person I expect if they're of type theta I and the strategies S are being followed? And we end up with a calculation which looks as follows. First of all, we can look at what the possible types are. So we're going to be summing, the person knows their type, then that can tell them something about what they believe the probability of other people's types will be. We're going to sum across those things. And the utilities are going to be evaluated with respect to those types. So that's one aspect of it. The second aspect is that they also have to do the calculation of what they then believe other players will be doing, or including themselves if they're mixing, in terms of which actions will be chosen as a function of the types. So they have a probability distribution over types. Then what are the strategies that are going to be played? With what probability are we going to see different actions? And then what's the utility of those actions? So we've got the payoff as a function of actions. We've got probabilities of actions. And we've got probabilities of types. Okay? And so that gives us an expected utility calculation, which then a player can use to evaluate what do they think a given strategy is going to lead to in terms of payoffs. That's the interim expected utility. If we move things back and then have to operate at an ex ante stage, then we can very simply say, what does I think the probability is that they'll be of different types, and what do they think their expected utility be as a function of those types? That gives you an overall expected utility. Okay, so we've got an ex ante expected utility, which isn't going to condition on types, and then an interim one, which conditions on types. Okay, in the ex post one, they know exactly what the types are, so they can just evaluate things directly as we did before. Okay, so the idea behind Bayes-Nash equilibrium or Bayesian equilibrium, the concept from John Harsanyi's work, is that we're looking for a mixed strategy profile. You can also, define pure strategy equilibria just by restricting this to be pure strategies as opposed to mixed. But what has to be true is that each individual should be choosing a best response. So their strategy S sub I, which is now a mapping from types into actions, should be maximizing their expected utility, here taken at the interim stage, so conditional on a theta I that they might see, and it should be true for every I and every possible type. So no matter what type I am, the strategy I've chosen should be maximizing my expected utility, given what I think other people are going to do, and given the expected utility that I'm calculating based on those strategies. Okay, so this is exactly analogous to Nash equilibrium. It's just taking explicit account of the fact that individuals will see different things at different points in the at the interim stage, and should be maximizing with respect to that information. Okay. The above definition, this definition we just went through, is based on an interim approach. So it's asking that every individual maximize with respect to the information that they have at the interim stage, and no matter what that information turns out to be. And if it happens to be true that every type occurs with positive probability, then this is also equivalent to just looking at the ex ante stage and saying, look, my strategy should maximize my overall ex ante expected utility, because if it's maximizing things for every possible theta, then it's also going to maximize things when I average across those thetas. And likewise, if it didn't maximize with respect to some theta and all the thetas are receiving positive probability, then it couldn't be maximizing overall. So you can write this Bayesian equilibrium down either from an ex ante perspective or from an interim perspective, as long as all types have positive probability. Okay, so what have we got from Bayesian-Nash equilibria? We've got an extension of Nash equilibrium to a setting, to the Bayesian game setting. It explicitly models behaviors in settings where we've got this uncertainty, but the concept is simple. Players choose strategies to maximize their payoffs in response to others, accounting for these two aspects of uncertainty. One is strategic uncertainty. What do I think other players are going to be doing as a function of types and uncertainty? And secondly, payoff uncertainty. I've got to be expecting over types, which might enter my payoffs. So it's capturing both of those elements. Hi folks, this is Matt here to tell you a little bit more about Bayesian games. So we're going to take a look at a quick example just to illustrate some of the concepts and to see, at least in a simple example, how you might think about solving one of these games. And later in the course we'll be talking a little bit more about auctions, so you'll have a chance to look at some auctions as well. Okay, Bayesian-Nash equilibrium. What did it do? Again, it has a plan of action for every player. So we have what they're going to do as a function of their information, their types. And it's maximizing their expected utility, expecting over what they think other players are going to be doing, and expecting over the types of other players which might affect their payoff. So let's look at a very simple example. So this is sort of a Hollywood-style example. So let's call it the sheriff's dilemma. So this is a very simple setting where you've got a sheriff and they're faced with an armed suspect. Imagine they've both pulled guns and they're standing there staring at each other with their guns in hand, and they have to decide whether to shoot at the other or not. We could do this in the Wild West, we could do it in a cop thriller, etc. But the idea is that you're faced with this dilemma: do you shoot or not when you're faced with the armed suspect? And in this case, let's suppose that the suspect is either a criminal with probability P or not with probability 1 minus P. So either they're guilty of some crime or they're innocent. And in particular, when we think about this, the sheriff would rather not shoot, would rather shoot if the suspect's going to shoot. So if you're going to get shot at, you want to defend yourself. but you would rather not shoot if the suspect is not. Even if it's a criminal or not, you don't want to shoot the person if they're not going to shoot you. If it's a criminal, you'd rather take them to jail. If it's an innocent person, you'd rather not shoot them at all. So the sheriff would rather not shoot if the suspect doesn't, but will defend themselves if shot at. And the criminal would rather shoot even if the sheriff does not. So this is a situation where if they'll realize they're going to be caught if they don't shoot, and so they're going to want to shoot. And the innocent suspect would rather not shoot even if the sheriff shoots at them, because they realize if the sheriff ends up shooting, they're going to die. Maybe they'd rather not shoot and be remembered for shooting the sheriff. So that's the setting of the game, very simply. Let's take a look at possible payoffs and the structure of this. So let's have the sheriff be the column player so they can shoot or not. And here, in terms of the representation, we can think of there's two different types of the player. There's the theta for the innocent suspect and theta for the guilty suspect. So they could either be the bad or good suspect. And this is happening with, so the innocent is happening with a probability 1 minus p, and the guilty is happening with a probability p. So this probability p, you've got this guilty 1 minus p on the innocent. And the sheriff doesn't know what the type of the individual is, the suspect is. Okay, so then we've got payoffs in here, and the payoffs reflect the basic structure that we talked about before. So in particular, if you're going to be shot at, if the sheriff is going to be shot at, they're going to get a better payoff from shooting than not. In either case, they'd rather, it's a negative payoff here. So actually, if you don't shoot and they're shooting you, that's a bad payoff. You're going to get killed. If you shoot back, you might end up hurting a person. In this case, they're getting a negative payoff because they're actually shooting an innocent individual, and so forth. So the not here is the best payoff for these individuals. For the when they're looking at a criminal, the guilty individual. Again, they'd rather shoot if the criminal's going to shoot. In the case where the criminal does not, they would get a payoff of 1 from actually capturing the criminal and taking them away and so forth. So we've got payoffs that we can look at, and you can study this in a little more detail. And then the question is, what's actually going to happen in terms of the play of this game? Okay. So what we can do is begin to analyze, okay, if we're faced with the good suspect, the innocent one, then what are they going to do? So let's first try and calculate what the suspect is going to do. And what we see here is that the suspect in this particular situation, conditional, once they see their type of being good, then they should end up, here they get a payoff of -1 if they shoot, 0 if they don't. So they'd rather not shoot. Here they get a -3 if they shoot, a -2 if they don't. So we end up with a strictly dominant strategy of not shooting if you're good. So essentially what that tells us is that if we're looking at for a Bayesian equilibrium, the good player, regardless of what they think the sheriff should do, should not shoot, right? So we can cross this out and say that the only possible strategy for a good player is that they're not going to shoot. Okay. Now we go to the bad player, and we do a similar kind of calculation, and basically the criminal is going to shoot in this case, right? So we look at 0 versus -2, 2 versus 1. That's shoot strictly dominates not for the bad player once they know their type. So that tells us that in terms of either an interim plan, or even if we go back ex ante and try and figure out what these players should do, basically the good one should not shoot and the bad one should shoot. And so now we've got a probability P down here, 1 minus P here, and we want to ask what's the sheriff's best reply. Okay, well, basically what happens if they shoot, what are they going to get? They get 0 down here, the sheriff gets a -1 up here, so they're getting -1 times 1 minus P if they shoot. If they don't shoot, what do they get? If they don't shoot, Well, they get 0 up here and -2 down here, so they get a -2 times P. And so we can think of the situations, when is it better to shoot, when is it better not to. And you can check here that if P is greater than 1/3, right? So if you find a point where these two are exactly equal to each other, that's going to be the point where P is equal to 1/3. If P is bigger than 1/3, then you're more likely to be down here, you're more likely to want to shoot. And if P is less than 1/3, then you would want to not. So depending on what P is, you're going to have Bayesian equilibria. So the Bayesian equilibria of this game are going to be for the good type, the innocent type, I guess. Innocent type here should always not shoot. The guilty type should always end up shooting. And then the sheriff, if P is greater than 1/3, the sheriff shoots. P is less than 1/3, they do not. And for P equals 1/3, any mixture for the sheriff. The sheriff can just flip a coin. They're completely indifferent between shooting and not when P is exactly 1/3. So we have a Bayesian equilibrium. In this case, the Bayesian equilibrium is going to be generically unique. It's going to be unique as long as P is not 1/3. And whether or not they decide to shoot depends on what their payoffs are. And so what one thing that this example illustrates, it's a fairly simple example, but it still captures the basic elements of Bayesian equilibrium. How so? Well, there's several things going on. First is that the payoffs of both players depend on what the type is. Okay? So whether the sheriff is getting a high or low payoff from shooting or not, exactly how it works depends on whether they're facing a good or bad suspect. And also that determines the strategy of the other player. And so there's both strategic uncertainty about what the other player is going to do, which depends on the state, and there's payoff uncertainty about what the best thing to do is for the sheriff based on the state. And putting those two things together, we get a Bayesian equilibrium, and we end up making a prediction. Okay. So this is a simple game, but it's going to capture a lot of things in terms of how players are going to make decisions in uncertain environments. And Bayesian equilibrium moves us one step closer to applications where in many games in the actual world, you have uncertainty in terms of what the payoffs are going to be and what other players are going to do. So, summary of Bayesian Nash equilibria. What have we got? It's a model that explicitly captures uncertain environments, and players choose strategies. Again, equilibrium notions, so you're maximizing your payoffs in response to uncertainty about both how other individuals are going to play and what the payoffs are from different actions. So it's a very powerful tool and one that has many applications, some of which we'll see in some of the added lectures. Take care.